Today we will talk about growth rates. Growth rates could be interest rates on money, could be the growth of bacteria, it could be the growth in the number of people with an infectious disease, which is quite relevant right now. So let's start with a very simple example. Suppose we'll talk about number of people infected. So I will use N with a subscript I, number infected. So just to begin with, suppose there's some very simple growth that 2 people are infected each week. So then at the end of the first week, 2 people are infected. At the end of the second week, 2 people are infected. At the end of the third week, 2 people are infected. At the end of the fourth week, 2 people are infected. At the end of the fifth week, 2 people are infected. And assuming for now that nobody is recovered yet, we could say that we simply have 5 weeks, 2 people per week, 10 total. So essentially, and if we use time, and we can use even a discrete number for time. So for example, we'll use time, the letter T, to represent the time. And the number that's growing each week is 2. So then 2 times T, very simple equation, the number at the end of T weeks, and in our case here when T is 5, the answer is simply, at the end of the 5 weeks, it's 2 times 5, 10 people infected. Very simple rate, same amount each week. Sometimes called linear growth, it's the same each week. We could write it as an equation that Ni equals 2 times T, which would be simply an equation for the variable N. As I said, I'll just put a little I on it. So Ni is 2 times T, and as T increases, Ni increases by 2 times T, so it would be essentially a straight line. N equals 2 times T, assuming 0 at the beginning, and so if you go 10 weeks, it would be 20. Very simple growth. Of course, in reality, growth is not as simple. And quite often, there are complex factors which lead to increase in growth, decrease in growth, changes in growth over time. The model that's of most interest, because in some ways it's perhaps the most dangerous in terms of, say, the current pandemic, and that is some kind of a more exponential growth rate. Suppose that we have 2 people infected at the end of the first week. But suppose everybody who is infected infects another person. So therefore, these 2 people infect another 2 people. So that means after 2 weeks, 4 people are infected. Now those 4 people infect another 4 people. So 8 people are infected. And then they infect another 4 people. So 16 people are infected. And they infect another 16. So at the end of 5 weeks, there are 32 people infected. So what would be a formula for that kind of growth rate? A formula for that growth rate would be, in terms of the time, that's 2. That's 2 squared. That's 2 cubed. 2 to the power of 4, 2 to the power of 5. So the formula for this type of growth rate would be Ni equals 2 to the power of T. simply each person is infecting another person. Therefore, there's a doubling, which is why it's 2 to the t. Notice then the dramatic difference. And let's just go on a little bit further just to look at it. Say if we went to 6 weeks, it would be 64. 7 weeks would be 128. Notice how quickly it can get out of hand. In other words, if you're doubling here, you're just adding 2, adding 4. That might be okay. Suppose you had a population of 1 million people. Then 8 people is manageable. Your hospital maybe has 1,000 beds. So everything is fine. 16, 64. But very, very quickly here, in the 6th week, it's 64 people. Still sounds manageable. But if you understand this growth rate, the next week it's 128 more. The next week it's 256. The next week it's 512. And in the 10th week, you're up to 1,024. And suddenly your 1,000 bed in the hospital is overrun. So it's important to understand this idea of exponential growth. We could look at this as well in terms of, you know, if we just drew a picture of it, in the very simplest sense, the picture up here for the 2t would have been something very simple. It would be basically something that looks like that, just goes up like that. Whereas here, your growth rate is something more like, because of this exponential type of growth, it's going to look something more like that, and up, 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 up very quickly like that. So that by the time you get to a 3, it's an 8. By the time you get to a 4, it's a 16. And suddenly the growth goes way up. Exponential growth has that kind of growth on it. To understand that, you basically need to simply understand exponents, how to get the powers of numbers. And you could look at these models and consider making a small change. For example, if you are modeling this disease and you see this type of thing happening, and you wonder what would happen if you could in some way reduce the infection rate. For example, you decide that each person does not infect another person. We'll say that maybe each person infects, we'll say, I know there's no such thing as a person and a half, but we'll say it takes 2 people to infect 1 new person. So let's explore that for a moment, see what would that look like. So then we would begin, we'll say 2 people have this disease. Now what happens if we have those 2 people infect 1 other person? So that would mean there will be a 3rd person infected at the end of that. So it appears after 1 week, it would be at the 2nd week, those 2 people have infected 1 person. Now we look at this and we think, well, now how are we going to do for, we'll say 3 weeks, the 3rd week? So 3 people therefore will infect another 1.5 persons, but there's really no such a thing as 4.5 persons. So we would have to modify our approach a small bit to look at this a little differently, because this proportion of going from 2 to 3 in 1 week, so even though there is no such a thing as a half person, we can just do this for the sake of the proportions. So 2 people leads to 3 people, leads to, technically it's 4.5 people. And then after that, it gets just kind of trickier all the time. So 4.5, and each of those, so apparently they will infect another 2 1/4 people. So I think that will get us to 6 3/4 people. So you can see the numbers get sort of awkward. But the question is, what would the formula look like in this case? The formula will look like, instead of being 2 to the power of t, the formula is going to be, since the growth rate, each time you're basically multiplying by 1.5, isn't that correct? 3, 4.5, 6 3/4. So it's 1.5 to the power of t. We're doing this rather slowly, but it's giving you an example of when you begin to modify something. But then let's look at that. 1.5 to the power of 0 the first week would be only 1. So I believe we have to multiply this by 2. So notice what we're doing here. We're doing a little bit of mathematics. We are trying to match. We have this formula, and we're trying to create the formula to, sorry, we have this set of numbers, and we try to create a formula that matches it. And we see, I believe that would now work, because if t is 0, 1.5 to the power of 0 is 1, so that's 2 times 1. 1.5 to the power of 1 is 1.5, multiplied by 2 is 3. Now 1.5 squared, that'll make us do a little bit of those proportions we said earlier, so I prefer fractions. So what's 1.5 squared? It is 3 over 2 squared, isn't that correct? 3 over 2 squared. 3 over 2 squared will be 9 over 4. 9 over 4, remembering from what we did for our fractions, 3 by 3 over 2 by 2 is 9 over 4. So then what would 2 times 9 over 4 be? It would be 9 over 2, which indeed is 4.5. So it appears that the formula in this case would be 1.5 to the power of t. Now, we probably have to use our calculator after this, but let's give it just one more attempt, and this would be again practicing your fractions and all of that. What is 1.5 times 6 3/4? Well, you get half of 6 3/4 and you add it to it, which is 3 3/8. So that should get us, I believe, 10 1/8. But notice here now, at the end of 5 weeks, 1, 2, 3, 4, at the end of 5 weeks, just about 10 people are infected. Let's go back here to this growth. That was 32. So you can just use that as an example to look at, if each person infects one other person, it's doubling, 2 to the power of t, and after 5 weeks, it's 32. After 6 weeks, it's that. After 7 weeks, it would be 128. Roughly speaking here, if this is 10, then after 6 weeks, it's about 15. And after 7 weeks, it's about 22. So reducing the rate quite dramatically, again, reduces it. Eventually, of course, as you get bigger, things get out of hand. But by reducing the rate a small amount, and of course, how do you reduce the rate? That's where the public health people will be telling you, wear your mask, which will reduce the rate. Instead of being a 1.5, it might bring it down to 1.1. And if this number is as small as 1.1 or even very close to 1, then you're back to something very simple where it's almost not growing at all and people are recovering as quickly as they are getting it. So that's just a brief snapshot of growth models, exponents, and simple linear growth versus exponential growth. And you can certainly play around with that. And you could look at factors. You could, more involved models could subtract the number of people who recover, subtract the unfortunate number of people who may pass away from the disease. All of these factors can be developed into creating more realistic models of the growth. And you can have as much fun as you like developing all sorts of models, and you can look on the web to find examples of different factors and how they affect it.